So today's topic is hashing. It comes from chapter 15 of the textbook. And long story short, I want to teach you today the sort of fundamental concept of how hash set and hash map are implemented. Do you guys remember the difference in terms of when you're using them? The difference between set and map versus hash set and hash map? Like, how would you summarize that? Just in terms of what they do when you interact with them, when you use them. Yeah, what's the difference?
Hash sets and hash maps are unordered, but also faster.
They're a little faster than the regular set and map, but they're unordered, as opposed to the sorted order of the regular set and map. Yeah, that's a pretty concise description of the difference. I want to try to show you why that is the case and what is actually going on inside the hash set and hash map. And so let's talk about set first. Let's talk about implementing a hash set. So remember, we basically know how to implement the collection, the Stanford Library collection called set. Right? You know how to do that now. At least you should. Do you remember how that's implemented? What's inside of a Stanford set? It's a binary tree, a binary search tree, right? Where you go left if it's smaller and you go right if it's bigger. And that's the internal structure that is actually being used in Stanford's set. So let's talk about implementing a set. Let's go back to that idea. Let's pretend that we're not going to use a tree. Let's try to think of a way to store a set in an array, more like a vector or something like that. So, OK, there are different ways we could do that. One is just we could, if you say you want to add these things to the set, then internally, the array of contents, we could just put the new thing that you have added at the end, right? So you add 9 and 23 and whatever, and it ends up in there. If you built the thing this way, you could totally implement a set that way, right? And the main three methods we're always going to want on a set are add, remove, and search, like contains. So how fast is it to add something if you implement it this way? What's like the big O?
1.
O of 1? Yeah, because you just put it at the end. It's only slow if you have to resize, and if you resize a lot, or if you resize to a double capacity array, you won't be resizing very frequently. So overall, it's O of 1. How about contains? O of n, because I have to look for it. I have to look at them all. We've talked about this kind of stuff before, right? How about remove? Also O of n, because I got to look for it to see where it is, right? So of course, you start thinking, well, maybe if I'm going to use an array, maybe I don't store them in this order. Maybe I do something else. Maybe I store them in a sorted order, right? That would be something that we could do. How long does it take to add something to this representation? You say n. Why does it take n?
Well, you have to look through and find the spot to insert it, and in the worst case, you'll...
Yeah, she says you have to find the place to insert the element, which could be anywhere from here to here. And once you find it, you have to shift everybody over to make room. You could use a clever algorithm like binary search to jump around and find the insertion point quicker, but you'll still have to do shifting after you find that, which could take up to n time if you're inserting something at the start, right? So overall, you're right. Adding is O of n. How fast is it to search this? Contains. Yeah?
You could get away with log n.
You could get away with log n. How is that?
But there's a search algorithm which is like divide it in two and like check.
Right, divide it in half over and over. That's binary search, right? I mean, a binary search tree is called that because you walk it in the same way as binary searching an array. You chop in half because of the sortedness, right? You look at the middle, and if it's bigger than that, you look at the right half. Otherwise, you look at the left. You know, that sort of business. You could do that. That takes log time. So searching takes log. That's better. You don't need to do a loop over the whole data. Log is a lot better than O of n, right? Remove, how long does it take to remove? I think it's n because, yeah, when you find the thing that needs to be removed, you're going to have to shift everybody again, right? So anyway, this one, the one on the previous slide, adding was really fast, but contains and remove were both really slow. This one, adding and removing are really slow. In fact, adding is slower, but contains is faster. So you might argue that this one might be better if we're going to be in a situation where I'm willing to pay some startup cost to build the thing, and then once I've got it, I'm going to search it a whole bunch. So if those searches are faster, that's helpful. So that might be a better payoff here for this representation. But we could do better. So let's think about other radical ways that we could store things in an array. Here is a very unusual idea that maybe we could use to represent a set. And it's got a bunch of problems with it. And we're going to talk about what the problems are and maybe see if we can fix them. So here's a weird idea. What if when they add a value I, store it at index I? So it's not sorted. It's not from the start over in the order of insertion. It's neither of those last two orders. This is like the value I gets put at index I. So if we did that, how long does it take to add something to this representation? I say add 3. You go to the slot 3. I guess it says 1s and 0s. I guess it could be booleans of true or falses or something like that. You go to slot 3. You set it to true. That means the value 3 is in this set. You understand? How long does that take to do that?
Big O of 1.
It's big O of 1. Because jumping to a certain index in an array is constant time on a computer. You don't have to like walk. It's not like a linked list. An array, you can jump to any index instantaneously. OK, yeah, question.
I thought that like since the array size is fixed, in the worst case you add something that's larger than your size, and then you have to resize, and then isn't it O?
Right. So she's concerned that this might not be the most airtight idea so far. And she said, well, like, what if I add like 29? There's no slot 29, so I would probably have to make the array bigger so that it had a slot 29. OK, fine, I do that. So that takes a little bit longer. What if they add the value 4,700,000 whatever? Now I have to make an array of size 4 million so I can jump to that index and put a 1 there or a true there. So yeah, that is memory inefficient, right? You're wasting a ton of empty slots just so you can put a little 1 way over there somewhere, right? But I mean, hey, let's just work with me here, you know, like maybe I know the numbers are like test scores or student IDs, and so I know they're all going to be in a manageable range or something. I mean, if you decide that you're willing to pay for the price of all that memory to have all those slots, then if I just jump to slot I store a number there to indicate that I've added I to this set. That might be fast, right? I mean, so yeah, you're totally right. That's a problem. If we add big values, we suddenly need a really big array. And it's not just that we need a really big array. Sometimes when you have a really big set, you need a really big array. Hey, that happens sometimes. But it's unfortunate to need a really big array to store like 4 values, just because one of them happens to be a large integer, right? That's silly. So it sounds wasteful. It's very sparse. But very fast, right? We could store things right away, just jump to the slot and put a 1 there. We could remove things, jump to the slot and put a 0 there. Contains is really simple, right? You just jump to the slot and see if there's a 1 there. If there is, then it's contained, and if there isn't, it's not contained. There's something to this, right? There's kind of something clever here. It's pretty fast, except for this like horrible memory consumption aspect, right? Well, here's a picture of like, hey, if you added 18s or 12s, you'd have to make the array bigger to fit them. That's kind of what you were on to. Again, the extreme case is you add a really big int. You know what the biggest int is, right? What's the biggest possible value that could be stored by an int? 2 to the 30, what? 32nd? It's 2 to the 31st minus 1, I think. Because it goes from positive to negative that much, roughly. Anyway, yeah, but it's up in that range. It's a couple billion. So in the worst case, I might need an array with like 2 billion or 4 billion elements in it. That sounds kind of crappy, right? OK, But maybe that means we scrap this goofy idea. But what if maybe we could kind of try to see if we could make this idea work. Maybe we could patch this idea into a place where it still had some of this cleverness to it, but maybe didn't take up billions of array slots of memory. Let's explore that. This idea is called hashing. Hashing is the idea of having a large domain of values and mapping them into some smaller domain efficiently. So right now I'm giving an example of a set of integers, and the integers that would be in the set could be any legal integer value. So it could be any 4 billion values. If only we could figure out a way to not need 4 billion slots to store them all, but still have some of this quick idea of jumping to the right place immediately. That seemed like a cool magic trick. You know, any algorithm where I have to like loop over things and look at all the slots, that sucks. If I could just come up with an algorithm where it just jumps to the right place like I had a second ago, that would be really cool. So an array that is being used in this way that I'm talking about, we sometimes call the array itself a hash table. So like in this picture right here, these arrays might be called hash tables. And the process of how you map from the piece of data to where to put it, the element value to the index of that element value, that mapping is called a hashing function. Now this thing on the previous slide here, the hashing function is very trivial. The idea is the hash code of the value k goes to index k. So it's just a, what do you call it, identity function, right? Isn't that what you call it? Just it spits out what you feed it, right? So hash code of I is I, okay? So sorry, I guess I just jumbled two terms, hash function and hash code. Hash function is the sort of mapping process from element values to indexes. And the hash code is basically the index that it spits out, what index to put this value at. Okay, so I mean, we're starting along this process of seeing if we could build a set using these ideas. And we started with like, put element I at index I, and it has these sort of major warts, has these major problems with it, right? Well, okay, what could we do? What if we had some small number of we sometimes call the indexes buckets, like we have 100 buckets or 10 buckets, and we want to be able to add things that are not in the range of 1 through 10 or 1 through 100, but we don't want to grow the array fully to be the size of, you know, if you add 4 billion, I don't want the array to have 4 billion indexes. Do you have any thoughts of where we could put it, or some modification to our mapping that might work out okay? What do you think? What if I knew that like almost all the data was going to be from 1 to 100, but occasionally there's going to be a really big number, but wasn't going to be very many of them? See, if you're watching on video, I don't think the SCPD footage really captures the awkwardness of the moment. Everyone's just quietly looking at me, blank stares. I'm not asking because I think it will give me this perfect answer. I'm just looking for ideas. And if your idea is silly or zany, that's fine. Maybe it just gives us other ideas. I just want you to come up with something we could do. I've got 100 buckets, but I want to sometimes store things that are not from 1 to 100. How might you store them?
You could have a multiplicative thing in there somehow, so that the last couple elements in there have some sort of multiplicative factor of 10 in front of them, or 2.
Okay, some kind of scaling or multiplication factor where like, now, but of course what always happens is if there's like 100 buckets and more than 100 unique values that might want to be put into those buckets, if you do any kind of like let's say there's 1,000 unique values and we're going to store it in 100 buckets somehow. Anytime you go from 1,000 to 100, you potentially run into conflicts of some kind, right? What if two people want to be in the same bucket? I mean, what's the analogy, I guess? Like, so what's some sort of fixed resource, like the shower at the dorm or a timeshare on a condo, or you both show up to vacation there on the same day? I don't know what, but there's some issues that could come up with a system like that. But I think it's a good idea, like maybe coming up with a way to shrink the range, multiply the range, divide it to where it does fit into the range of numbers that we had. So what if the array had 100 buckets and I have 1,000 numbers that I can fit? Or let's make it real simple. Let's say 100 buckets, but there's 200 numbers I want to store. Maybe the numbers 0 through 99, I just put in, you know, that same bucket, bucket I. What about the numbers 100 through 199? Sorry, what?
Bucket of size 100 in that last bucket?
Oh, like attach another array? Well, the only problem with that is that then I'm going to have 200 total buckets. I'm trying to come up with a way to have fewer buckets than values, but I'm sort of relying on the fact that hopefully I won't have to add all 200 of them. Hopefully it'll be sparse enough that I'll be able to get away with it. What were you going to say? Yeah.
Maybe you have like 100 and you want to put them into 10 buckets, like put all the numbers that end in 9 in like the 9 bucket and all the numbers that end in 5 in the 5 bucket.
Okay, maybe like small groups. You know, I let you guys work in pairs. Maybe I'll let these elements work in pairs. Maybe I'll have the value 0 and 100 both live here. The value 1 and 101 live here. The value 2 and 102 live here. All the way up to 9 and 199 live in the last slot. Or 99 and 199 live in the last slot. I don't know, something like that. Some sort of simple thing where like, if you're bigger than the array size, maybe I'll just wrap you around to the start again or something like that. And so now maybe each bucket stores one of those two values or somehow shares and they could store both or something like that. That's kind of what we're looking for. Yeah, so let's keep walking down this path a little bit here. So here is a little bit better hashing function. So originally we just had hash code of I is I. So let's make two quick fixes. One is if the I is a negative number, let's absolute value it. So that, because you can't have a negative array index, right? So let's just throw away the negative sign. So if you try to add a -2, I'll put it at 2. And then the second quick fix is basically what you guys are saying, which is I'll just like store, in this case my hash table has 10 buckets, just for it to be simple. I will store the value I at the length of the array, at I mod the length of the array. So I'll wrap it around. So, I mean, yeah, in this case, I'm literally just talking about like, well, if it ends with a 7, put it in bucket 7. If it ends with a 9, put it in bucket 9. This new hash function now does map every int in the world into some bucket from 0 to 9, right? There's no int that I could feed to this thing where it would spit out a value that wasn't between 0 and 9, right? So that's a good thing. But what's the problem with this? I mean, how do you bust this as described here? Yeah, go ahead.
Like if you had a 49 and a 59, we both kept in one spot.
Yeah, like if we try to add 59 or 79 or whatever, the slot's already taken. So it's a problem, right? I mean, we could deal with it. It's just right now it's going to be a problem because we either don't add it, which is bad because we just didn't record the data that they told us to add, or we add it and we clobber some other pieces. Neither of those things is good, right? So, OK, real quickly. Oh, this is listed as a Socratic, but I'm going to just ask you this one. So like that's the hashing function, right? You just jump to the slot in the array. So add basically, I mean, these functions get really simple. Go to your array, go to hashcode I index, set it to I. Contains means if the value stored there is I. And remove means put it back to 0, right? I mean, these are so easy to write. They just take a second. Do you understand that this would be the implementation of add, contains, and remove if you did it this way? OK, but we still have that problem we had a second ago. I think the Socratic says what's the runtime, but we talked about it already. It's big O of 1, right? The answer is A. It's big O of 1. So that's why I'm not going to ask you. OK, but the problem is this collision business, right? You add 24. It goes there in index 4. I later add 54. If I didn't think ahead, oops, I clobbered the 24. So anybody who's coming up with one of these collections, which we're calling a hash set or hash table, has to come up with a way of dealing with these collisions. Well, so what do you do about them? You have to do something. There's lots of different strategies for what we call resolving collisions, collision resolution. One strategy you could use is just put it in the next bucket. If I add 24 and then later I try to add 54, I go to the slot for where it should go and I say, oh, this one's taken, and I just go to the next one. This is probably what you do with your locker at the gym or something, right? Like, you've got locker 54 reserved, and some asshole stole your locker. And so you're like, well, fine, I'm going to take locker 55 and screw whoever's locker that is, because somebody took my locker, or your parking spot or something like that. We use this algorithm in real life all the time, right? Of course, now we're causing a problem for that person, and they go there. And it's just, that could be a sort of a domino effect, right? But this is one way that you could deal with this. It's called probing. If you just jump to the very next bucket, that's called linear probing, going to the very next bucket. Sometimes you jump to some other bucket. There's ways where you jump by larger amounts. That's called quadratic probing, where you jump farther away to help avoid clumps. But we're not going to spend a ton of time on that. So what do you think of this? What do you think of this as a collision resolution? Like, what impact does this have on our algorithms, on our runtime? We have to modify our code a little bit if we did this, right? What are some things we would have to do? Like if I asked you later, I'm doing this now, and you add things, I'm going to potentially do this stuff, this probing stuff. Now later, if I want to ask to see if you contain something, do you contain 54? What's the algorithm for that now? It used to be go to index 4, right? What's the new algorithm sort of going to be? Yeah?
Go ahead.
index 4 and then keep going rightfully down 54.
Yeah, thank you. She said start at index 4, just like we would have originally. And if we see the 54 there that we were looking for, then great, fine, stop. OK, contains returns true. But if we see something else there that isn't 54 and also isn't 0, keep going, like you said. Keep going forward and see if we find a 54. We either stop when we find a 54 or we stop when we get to, I think, an empty bucket. That would be a sign that the clump is finished, so it isn't there, right? So that's not that hard to modify our code to do that. Hey, Kevin, do we have hours today?
Yeah, 6:30 in Hewlett. Same room it always is.
Hewlett 102? Wait,
Something like that.
I think I actually have it on the website, but my brain is turning into mashed potatoes slowly. Yeah. There it is, Wednesday, May 27th, 6:30 p.m., Hewlett 102. So yeah, if I read my own website, like I always tell you guys to do, then I would have known that. Oh, well, fine. Thanks, Kevin. So anyway, I'm just saying, you could patch up your algorithms to accommodate this, and it would still work, right? Did you have a question? Yeah.
Yeah, I thought, could you, instead of storing the actual integer value in each of these, you could store in each entry, you could, well, I guess it expands your memory use, but I was thinking you could store a vector of ones or zeros, booleans, such that the lowest entry would basically say, well, this is, mod, it's less than 10. The second entry would be it's between 10 and 20. The third entry would be it's between 20 and 30, and
Okay.
4 or whatever.
I think you have an interesting idea there, kind of a kernel of something smart there, which is that, well, I mean, sorry, that sounded rude, I guess. It's an insightful observation. I think, as stated, it would have some issues to implement, but I think there's an idea very similar to that might be really successful. He's talking about maybe this is kind of goofy. Maybe instead we could somehow just put them both in index 4, maybe in some kind of collection in a vector or something like that. I think it's a really good idea, and we're going to talk about that, something like that, basically in just a second. So give me 1 second. We'll come to that. Anyway, I'm just pointing out you could do this. And some people implement hash-based data structures that do this, and it's fine. The biggest problem with this is what? Like, what's wrong with it? Yeah.
If you try and put more elements in there than you have items, you can't do it.
OK, if you put in too many items, then these clumps get really long. And then I think what happens is, I mean, at some point, the whole thing gets full. But maybe we can fix that just by growing, making it bigger. We could deal with it. You're right. If we let it get totally full, it would be busted. Because you'd look for stuff, and you'd wrap all the way around. And that would be bad. But if we sort of resize it as needed, we would probably be able to avoid that. But still, even then, if it were mostly full, I think what you'd find is that you try to look things up, but then you have to walk a bunch of squares every time. And then the whole point of this implementation was that we could just jump somewhere and get the answer quickly, right? And that we're kind of not getting that anymore if everything's all clumped together and we have to loop over all these clumps to answer the question. So I think you're right. Like, the more stuff you put into this, the worse it starts to work and kind of breaks down. So a different idea, oh, sorry, this slide is just saying the clumps. They're called clusters. They clump up. You look up something. You might have to look at like 6 or 7 out of the 10 slots. That defeats the purpose of the whole idea. So a different idea, which is basically what you said, is just figure out some way to store multiple elements in one bucket. And you could either do it by something like a vector in the bucket or a linked list in the bucket. In practice, they usually use a linked list. And the reason for that is because it is easy to just insert something at the front of the list. It's easier to do manipulations on. It just turns out to be faster, I guess. This idea is called separate chaining. The reason they call it separate chaining is because each little bucket has a chain of all the elements that ought to go in that bucket, and they share. So now, if you're writing the algorithms for adding and contains and remove, if you want to add something, I think, do my slides talk about this? Yeah, so let's talk about if you did this. I think this overall is better than the other one, better than the probing one. And if you added to this model, where do you think you should put the new node? Like, I've got 54 and I've got 14, and I'm going to add 24. Where do you put it? I mean, you put it in bucket 4, but like, where among the others should I put it at? I mean, I could put it here, or I could put it here, or I could put it here, right? You want it first, I think. You want it here before the 54. First of all, it doesn't really matter, right? Do you understand that? They just have to all be there. If I ask whether it contains 24, you better say yes. That's all that matters, right? So it doesn't matter in any sense of, there's no right order. It doesn't have to be in any certain order. I just got to put it in there somewhere. If it's a linked list, you should know by now that if a linked list has a front pointer, the fastest place to add to the linked list is at the front, right? At the end is the slowest. You got to walk next to the end of the list. I don't want to do that. That's slower. I want this thing fast. So I just insert it at the front and make his next be 54, right? So that's the right place to put it. So adding takes how long? Big O of what? It takes big O of 1. Do you understand? Because the tasks here are figure out the right bucket, which is just some constant function mod 10. OK, this one. Insert it at the front, which is just a couple of pointer rearrangements. That's O of 1. Done. That's it. Add is O of 1. How long does it take to do contains? Like if I ask you, does it contain 14? What does the code have to do now? Yeah?
Worst, like all of the elements will be like at 4 and you have to walk to the end.
So she says worst case, isn't it O of n? Because what if all the things I add to this happen to end with a 4, right? Now I have this long linked list. When I'm asking whether the hash set contains an element value, I got to loop through here and like check all these nodes to see if they contain a whatever the value is, right? So worst case, maybe that would be O of n. Uh-oh. Well, so I guess what I would say is if your data is distributed nicely, that probably wouldn't happen, I hope. And maybe what you could do is instead of picking a hash table of size 10, which is easier to understand on a slide when I'm explaining it to you, maybe you could pick a hash table of size like 137, where A, it's a little bigger, and B, the wrapping of that is weird. And to happen to have numbers that are all congruent mod 137 is ridiculous. So you know what I mean? Like statistically, that's unlikely to happen. And maybe if it does, I'll reconfigure the thing so I pick a different mod of 248, and maybe that's even less. You know what I mean? Like just pick some other size of the thing so that the modding doesn't work out. I bet I could unjumble that if I had to, you know? Anyway, that's add, and then contains just looks through the list. And so if you know that the chains here are short, that shouldn't take too long. It's sort of like big O of however long the average chain is, which if you assume the data is distributed pretty well, it's not that long. So you kind of wave your hands, and there have been studies on this that they basically can conclude that it's O of 1. The chains are really short. Usually it's 1 element or 2 or 3, and that's about it at the most. And then remove is kind of the same thing, right? Remove is like look through the chain, find it, and then move the pointer around him, skip. It's linked list removal, right? You know how to do that. So remove is if these chains are short, remove is also O of 1. So it works out as long as the chains are short. OK, so that's where we add. Yeah, fine. Contains operation. What I talked about. I guess I should have been advancing my slides while I was blabbering this whole time. Contains just loop through the chain. Current, right? It's just, these are linked list operations. You know how to do these. And then remove is just, oh, I want to remove 54, so make current point there and make current the next point around him, right? Just, you know how to do all this stuff. That's it. That's how you do it. That's how you implement this thing. So after all that, I want to try to do that. I want to try to implement some of these things with you guys. So let's write a hash set that has add, remove, and contains, and maybe clear if we have time. OK? So let's jump to Qt Creator. And I've got a file called hashset.cpp and .h. And hashset.h just declares there's a class called hashnode. Hashnode is basically a linked list node. It's got a data and a next. It's just exactly the same as linked list node, right? That's all. We're just going to use this for those little chains that we're going to make. I just called it, I guess I could have reused the list node from before, but I wanted it to have its own name, I guess. And then hashset has a constructor, a destructor, add, clear, contain. It has some methods. None of them are written yet. So what we do need to decide is what are the private variables that the thing needs to have. So Tell me some variables that need to be in here. Like the private member, fields and stuff. Yeah?
Pointer to your array and the size and capacity.
Okay, the array and the size and the capacity. That's exactly what we had with the array list, and you guys array and heap-based priority queues have pretty similar variables. So in that case, you had like an int star for your elements, and you had an int for your capacity, and an int for your size. I called it my size, I think, because there was a method named size, and those can't have the same name. We're not going to do an int star. An int star is basically an int array, right? This array is a something star. What is it a star of? What is it an array of? Do you know? What would you say? Yeah. It's an array of hash nodes, so it's like a hash node star. That's slightly wrong, but very close to right. What's stored in each bucket of this thing? It's a pointer, right? This is an array of pointers. It's 10 pointers, 10 fronts, if you want to think of it that way. A linked list has a front. This thing has 10 fronts. So it's an array of pointers. So if you could somehow use brackets, you'd say like it's an array of hash node pointers, but you really say it like that. It's not a pointer to a pointer. It's an array of pointers, but we say, well, I don't know what I did there. You use star as pointer and star as array. So it's hash node star star. Elements, capacity, size. Now, in the constructor for this thing, we have to set the elements equal to a new hash node pointer array of size, what, like 10, I guess? Okay. I could even parenthesis it to null them all out. That would be fine. And then capacity is 10. And my size is 0, right? Destructor, we're probably going to delete the elements or whatever. I'll come back to that. I think there's more to that maybe, but we'll think about cleaning up our memory in a few minutes. Okay, add. So now remember what we're doing when we add a value. We're jumping to the right bucket and putting it in the little linked list for that bucket, right? So how do I know what bucket it goes in? Well, that's the whole mod hashing, value mod capacity or something like that, right? Like that's kind of what we're doing. But I thought we were going to be writing that a lot in our code. And so I actually went ahead and made a thing called hash code. You pass me a value, and I'll return you the index to put it at. And so that is just, did I write it already? Wait, is it there? Jump. It's not there, but we should write it. So the index that you store a value at is the value mod the capacity, but we made 2 tweaks to that. Do you remember the 2 tweaks? Or I guess that's one of the tweaks. The other tweak was we did absolute value, right? Or I guess it's absolute that mod there. Does that look okay? Right? So this is going to return a value between 0 and capacity minus 1 inclusive. Okay, so let's go back up to add. So usually what I do is I do something like int bucket equals hash code of this value. That's the index they want me to put it at, or that I want to put this value at. So I'm trying to do this. I'm trying to do this right now. Yeah? It's adding to a linked list. I think you guys have done that. Can you help me implement that here? Tell me some stuff I might need to do here. Yeah?
You need a pointer to a new hash node.
I need to make a new node, right, to store the new value that I'm adding. So like make this thing here, right? Okay. So hash node, new node is a new hash node that stores this value. Okay. Now I've got this guy, but he's not attached to anything. So what else? Do you want to continue from there? Yeah, go ahead.
Have your new node point to new node next should equal front of bucket.
Okay, yeah, whatever's currently the first.
Whatever bucket is pointing to.
Yeah, whatever that bucket is currently having as its first element, I want this guy's next to be that, right? So I want the new nodes next to be the element array at that bucket. You might say, well, do I say like front or something? I mean, the element array bucket is the front. Like that's the pointer of the front. So for him to say that the next is that means he'll point to what this points to. If this points here, then his next will point here. That'll do that. That'll hook that up. But now I have to put him at the front. So I'll say elements bucket equals the new node. Does that make sense to you guys? Attach him at the front of the existing chain. You might say, well, in linked list, don't I usually have to have if else's? Don't I have to check for null, this kind of stuff? I think if you look at the code long enough, what you'll conclude is that I don't need some of that here because I'm always inserting at the front. So it's like there's no else. It's always at the front. And null is not relevant because if the original value of this bucket was null, then I'm going to set my next to null and replace the null with me. So it'll put me with null after me, which works. It'll work out. The null is not going to break anything, I think, here. There is one other thing we should do, just a little thing, a little upkeep kind of thing. You know what we're missing here? When you add something, yeah?
I also want to check that that element isn't already in that list.
That's a great point. So we don't want duplicates, right? So we probably shouldn't do any of this if we already contain that value. We don't want duplicates, right? So what I'll do here is I'll say, well, if I don't contain this value, then do all of this stuff. However, contains is not yet written, but we will assume that we will be writing it in a moment, and hopefully contains will stop us from doing that sort of stuff, right? Now, if you'll permit me, I hope I remember this correctly, I think the testing code, I wrote a method before class called print structure or print table that just prints a nice little drawing of the hash table. And I did that so that we could just see visually what is happening. And if you look, I commented it out. I will uncomment it. Did I use the same variable names? Capacity. Yeah, basically, this is just a piece of code that for each bucket makes a current pointer at the front of the bucket and then loops until it's null, printing the nodes. And just this prints the hash table. You'll see what it looks like in a second. So I've got a main that adds some stuff and prints the hash table structure before and after it does it. This is like a debugging method just for us for class here. So if I compile this, load factor, what's this? Wait, hang on. I think there's something here that, there. OK, I think there's something in there that we didn't write. So, OK, let me run this. So here's what's happening. It says, I'm going to add 17, and this is your hash table before. They're all null. And I press enter, add 17 after. Now the front of that is this thing. So now I'm going to add 41 after, add 9 before, should be the bottom, right? After, add 29 before, after. So I put it at the front, add 37 before, after, add 81 before, after, add 69 before, after. So do you kind of see what it's doing? I mean, this is working, sort of, right? 20 before, after. OK, yeah, fine. So we are adding things. That's good news. Let's do contains. Let's do contains method. Unless there's a question so far. Did that make sense, like this add code? I mean, you could just see by looking at it that it's going to be O of 1, right? Just like this is it. There's no looping here. I guess the only part that you might question is contains, because that's a method call. If that took a long time, that could hurt our runtime. But this body here is not very slow, right? So O of 1, good times. Let's write contains here. So how do you do contains again? Well, we talked about it a little. Go to the bucket and look at all the stuff in the bucket. And if any of them stores the thing that they're asking about, then that's contained, right? I mean, that's kind of the idea. So a lot of these functions, you'll start out by asking what bucket to go to. So go to this bucket. How do I look at all the stuff in the bucket? I can't say if elements bracket bucket dot contains. That doesn't work, right? There's no methods there because elements bucket is the front of a linked list, right? So I want to know if that linked list has this value in it. So how do I look for something? What kind of stuff should I put here? Well, we got to walk around in a linked list, right? How do you like walk a linked list and look at it? Yeah?
You can set like another pointer, maybe current, and then at the front of the left. And just see.
That sounds great. Make like a current pointer at the start, and then just look at each one, walk through it, see if I see that value that they're asking me about. So let's do that. I mean, you guys have done that before in your assignments and stuff, right? So hash node pointer current equals front is like what? Elements bracket bucket? Bucket. And then while current isn't null, I will say if current is a node that stores a data that's equal to this value that you're asking me about, that's like current data would be here, current data is 54, current data is 12, I'm asking, or 14, is it the value that you're asking me about? If it's that value, then what, return true, right? You contain it. If I get all the way to the end and I get to the null, the end of the list, and I didn't see that value, then your chain doesn't contain that value, so I say false, right? I don't have to look at any of the other chains, it won't be there. That's it, that's contains. And actually, if I want to make sure that that works, I don't think my main was passing any duplicates, which it should, right? Oh, sorry. Do I need to say? Yeah, you're totally right. She says I need to write cur equals cur next. How many years have I been doing this? I still can't write a linked list traversal. Oh, well, thank you. That's good. Up here, when I'm adding these things, let's do like some duplicates. Let's see if it notices that, that 41 and 9. Or let's do these. Let's add them again and see if it adds them. Too many. What? Oh, 16. Let's try again. Let's try again. So add 17 before and after. That's fine. Add 41 before and after. Add 9 before and after. Add 29 before and after. Add 41. It's already got that. It shouldn't do it again. After. Didn't do it. OK. Add 9 before. After. Didn't do it. OK, so we're doing better stuff now. It's not adding duplicates. That's good. OK, so contains looks like it works. I'm willing to trust that. Remove is a little bit harder because, you got to do all the linked listy stuff like James Bond, be back by 1, train car, that kind of stuff. I think we could get it to work. We have a few minutes left. Let's do remove real quick. Remove this value. Pretty similar stuff. Go to this bucket. This is going to have that sort of if-else structure to it, right? Because if you're removing something from a hash from one of these linked lists, you either have to get to the node before it and point the next around it like that, right? Or what's the other case to consider? I mean, I guess there's a case where it isn't found, but I mean, there's another found case that we might have, yeah. If it's the front one. So like if the front node stores it, we can't use next arrows to get around it. We have to say the front should be the 54 instead of the 24. So I think what you do is something like, if the elements bracket bucket, so actually I think one thing that might be nice would be to say like, if I don't contain the value, then I'll just return. That's a little bit inefficient, but it helps me avoid a couple cases here. Like if the bucket, so if I get to this part, I know I contain the thing. So if the bucket itself, the first bucket, if his data is this value, then I need to remove the first guy. So I'll say something like elements bucket equals elements bucket next. Move him to the next. That's removing first element in a chain. Otherwise, I'm going to remove not the first element in the chain. So I think what I would do is something a little bit like this. Make a current that starts at the front, and then while something, I'm going to keep moving forward, right? But I need to James Bond this thing. I need current to be at the 24, and then I need to notice that the data next after me is the 54 that I'm trying to delete, right? So I need to adjust my tests and my cases a little bit. So I think I want something like, while current next isn't null, if current next data is the value, then aha, remove current next. James Bond, right? Right? It's that kind of stuff here. How do I remove current next? I just make the pointer go around him. We've done this before. Current next equals current next next. Just point around him. I didn't free my memory So I think I'll probably just do that after class, but I would make a trash pointer here. And, we've done trash. Fix this, then delete trash, that kind of business, right? There's one important thing here that's missing from this code, which is if I just added a whole bunch of stuff, this thing would get really crowded, right? Because there's only 10 buckets, and everybody's going to go into one of the 10. So if I have a whole bunch of elements in here, these chains end up getting really long. And then all that business about O of 1, that kind of falls away. So what a lot of hash tables do is they do something called rehashing. When the hash table gets too full, they grow it, just like you would with an array list or something, you grow it. I hope you can see, unlike with an array list or a heap or something like that, you don't have to grow it, right? With the array list or a heap, you run out of space. There's just nowhere left to put anything. This thing, you don't have to grow it. You just get these long chains. It's like if you don't cut your fingernails or your nose hairs or something for a while. You could get away with it, but it just gets unmanageable after a while, right? You know what I'm talking about, especially the older gentlemen in the classroom. Anyway, you don't have to resize, but resizing is good because resizing can shrink your length of your chains. Do you see why? Because if I had 24, 54, and 14 all in the same chain before, because they all had mod 10 equals 4, if I go to 20, now we're doing mod 20. So 24 is over there, and 54 and 14 are over there. So I split the chain up a little bit. You see that? So it actually makes the chains smaller, which helps avoid these long clumps that we wanted to avoid. So I'm out of time. Have a wonderful afternoon. Go to your